Hey guys, welcome to the lesson. At no time in any of our studies working with Cisco systems are we going to be tasked with understanding details about how devices interoperate than we are here in the confines of CCNA. Now we need to recognize the fact that there are different ways to do this, and Cisco does the descriptions just like the rest of the industry standards bodies based on something referred to as reference models. Now a reference model outlines a number of things, but the main object that I want to talk about right now is going to be how we are going to support the idea of host-to-host communications. Well, first of all, what is host-to-host communications? Well, if we were to say I had two laptops, and I wanted to use those laptops to share information across my infrastructure, excuse my crappy drawings, what I would do is I would notice, first of all, that I'd have some type of connectivity between these devices, i.e. Ethernet. Could be wireless, but for the purposes of our conversations, let's just say Ethernet. Now, recognizing that these devices need to be able to exchange information, what Cisco and what the industry standards bodies did is they came up with a number of reference models that govern how that communication takes place. Remember, I described the OSI model as a set of guidelines. Well, there are other models. There's the OSI model, the Open Systems Interconnection model, and there's the TCP/IP model. Let's delve into exactly what is involved in each of those and how they're going to work together to allow us to exchange information between our devices across the network. Now, what we have to recognize, first of all, is that there really are only two models. All right? Whether or not we recognize the fact that we have the OSI versus the TCP/IP is irrelevant. At this point in our conversation, what we have to look at is the way things were when I first started coming up in networking. The first thing that happened in my deployment was we had a company, I was working for a bank, and they had bought all Hewlett-Packard computers. And Hewlett-Packard had their own network card. It was called VG100 at the time. And it used in-way handshakes to be able to communicate to determine the maximum amount of speed. But the problem was they bought these devices and they were using Wellfleet back in the day. It became Bay Networks over time. I don't know who it became now. It's probably not even in existence. But the main point here is that they hooked all of these devices up and they didn't communicate. And it was catastrophic. I mean, people lost their jobs as a direct result of this. And that defines the way things used to be in the confines of setting up our system. So the old model, quite seriously, was, let me grab a black pen. The old model, quite seriously, was no rules. So if I wanted to have two computers, HP, talk to an IBM, couldn't do it. I had to have HP communicating with HP. And guess what? If I was running multiple devices and I had to have a bridge or a switch in my topology, it had to be HP2. And what that did is it meant that these companies could all make solutions that were proprietary to their own architecture and design. And the issue became, you were trapped, you were locked into a particular provider. So if I bought HP 5 years ago and Dell, as an example, were cheaper today, I couldn't buy Dell computers and hook them up. Why? Because of the fact that we had this proprietary infrastructure or this proprietary design. And it not only included the card, it included how the particular protocol stacks would interact on the card. So the industry standards body come up and said, you know, this isn't good. In fact, this is actually horrific. So what they did is they mandated the fact that they wanted to have a standards-based model. That standard-based model made certain that no matter if I had HP or IBM, they could communicate. Why? Because each of the manufacturers had to follow the same rules. That was the whole idea behind the standards. And they did this for multi-vendor support and they did it by creating what's referred to as a layered architecture or a layered model. Now this layered model, it lends itself very, very well to ensuring that we do the same thing. So if I decided tomorrow that I wanted to open up a business building network cards, all right, the rules, if I follow those rules, would ensure that my network cards would work with Broadcom, Intel, IBM, QLogic, Emulex, any of those guys out there. My network cards would be able to intercommunicate. I remember in the early days, I had an issue with Kingston network cards. They didn't communicate to Cisco switches. They would if you hardwired them, but it was an auto negotiation. The auto speed negotiation wouldn't work back in the day. And again, it's this idea of this reference model approach that they designed that is going to govern the fact that we can now drive multiple vendors to create interoperable devices so that now we're not locked into one provider. And the way that that was implemented was going to be with two models. The two models that we're going to discuss here shortly. The OSI model, the International Standards Organization, so that's the IOS, the International, ISO, excuse me. International Standards Organization Open System Interconnection Model, and the TCP IP model. Now what we're going to find here is the Open Interconnection model, the OSI model, is a 7-layer model, and the TCP model is going to be a 4-layer. But what I want to do right now is I want to explore this notion of the 7-layer model and what it actually defines and describes for us with regard to how we implement. And what we're going to do is I'm going to start this from the very bottom. Now, first, Cisco's going to want us to do a few things. One, we're going to have to be able to represent or regurgitate what this module is. And notice each one of these layers has a name: application, presentation, session, transport, network, data, physical. Now it may sound childish, but there is a mnemonic that I've always used to keep these in my mind, even today as a CCIE. And that's going to be all people seem to need data processing. That's from the top down. Another way of memorizing it is if you go from the bottom up, layer 1 all the way up to 7, is please do not throw sausage pizza away. Whoop, cut my hand off. So those are going to be useful mnemonics. I'll go ahead and write those down just so you'll have them. The first one is going to be all people seem to need data processing. So it's application, presentation, session, transport, network, data link, processing. I'm sorry, physical. And then the other one was please for physical, do for data link, not for networking, throw for transport, sausage for session, pizza for presentation, away for application. Now, with that all being said, that's just a mnemonic that's going to help us memorize exactly the orders. And Cisco's going to task you to do that. In fact, this would make a perfect drag and drop style question. If I was going to do a test, I would want you to be able to illustrate that you understand what each of these components are and how they fit into the grand scheme of things. But that doesn't tell us what they are and how they operate or how they work. And that's what I want to look at right now. Let's go from layer 1 up. So the physical layer. The physical layer quite literally governs all of the electrical and mechanical rules. Now the electrical and mechanical rules are important because it's through the use of these electrical impulses at layer 1 in this model that we're going to be sending messages. It all ultimately gets serialized onto the line. Whether it's a fiber optic connection or an Ethernet connection is irrelevant. If it's an Ethernet connection, it's going to be voltage. It's going to be logical ones and zeros represented by ranges or variances in electrical current. If it's going to be fiber optic, it's going to be pulses of light. The absence of a light being a 0, positive, or presence of light being a 1. So that's how we translate or transfer ones and zeros. Ones and zeros. So the next solution is going to be the data link layer. So let's look at what the data link layer does. The data link layer is very important for us because what it does is it actually defines how data is formatted. So data format. Now, and it's going to be specifically formatted for transmission across whatever media we have. The physical defines the media, but the data link is what defines transport. And what that's going to do is it's going to give us some idea of being able to deploy some features. Of those features, we're going to have error detection. As well as error correction. We'll talk about the nature of those later on in our conversations. But it's at layer 2 that we embrace our connectivity methods. The two most common methods of layer 2 that we're going to be working with is going to be Ethernet and serial connections. And to be perfectly honest, serial connections are kind of going the way of the dodo. Because what ends up happening now in our live working environments, we're using Ethernet as a WAN topology through advances of MPLS, through any transport over MPLS, through, let's see, another solution would be dark fiber, and also Metro Ethernet. So let's never forget Metro Ethernet. So looking at all of these solutions, they all plug together to create a scenario that allows us to be able to operate at these different levels. Now the next level that I want to talk about is going to be this network layer. Now in the confines of our studies, the majority of what we're going to be talking about is going to take place here. And this is going to be routing and switching. So switching is a data link tool and routing is a network level tool. Now when we have networking, we're going to be transporting IP TCP, or TCP IP, sorry. Transmission Control Protocol, Internet Packet, or Internet Protocol. And down here we're going to be pushing something referred to as frames. That's going to be in correlation to Ethernet. And we'll talk about that shortly. But the main thing also we want to look at is let's talk about network, the network layer. Now honestly, the network layer is where the magic happens with regard to our CCNA, CCNP, and CCIE studies. It's going to be that where what happens here is that it's going to provide connectivity and path selection. So connectivity and path selection. Now connectivity and path selection is extremely important because it's through the concept of connectivity and path selection that we can communicate between separated networks. Separate networks. Now when I say separate networks, I'm talking separate. I'm talking about one here in the United States, one in China. It's going to use the network layer to be able to communicate. And it's going to be through this deployment of IP protocol, IPv4, IPv6, and TCP, Transmission Control Protocol, IP, that we're going to be able to have all of this communication takes place. Now predominantly at the physical, not the physical layer, but at the data link layer, since we're working with Ethernet, we're going to be working with network interface cards, and that means we're going to be working with burned in addresses. At the network layer, that's where we are going to be deploying our logical addresses. So when it comes to data link, it's our MACs. So it's going to be our physical or burned in addresses. When it comes to networking, it's going to be our IP addresses or our logical addresses. Now, it doesn't end here, because what ends up happening is each of these layers provides services to the upper layer. So notice here at networking, I'm going to be using the creation of packets, and I'm going to be ensuring things like connectivity and path selection. And I'm going to pass information down to layer 2. Layer 2 is going to get that ready to go out over my Ethernet or my serial connections. Then ultimately it's going to get passed down to the physical layer where it's going to get turned to those ones and zeros. So you can see each one of these layers provides services to the other, ideally to the layer above it. Now with networking, the other solution is going to be transport. Now transport's a really interesting critter for us because it's something else that we're definitely going to want to understand. And what it's going to do is it's going to basically do one thing. It provides services. Well, Terry, what services does it provide? Well, the transport layer provides services that are used to segment, transfer, and reassemble data. So as we move information down this model from the application layer, we need to make certain that at each level we prep the data or the information such that it can be handed off to the next layer to ultimately be sent across a wire connecting another device. That's why we're talking about this in the confines of host-to-host communications. So if I have an image, let's say I have a picture, and I want to, that's on my computer, and Bob is on another computer, another host, and he wants to look at that picture, it's going to have to get passed down my model, and then it's going to have to come up his model such that whatever application we're using at the application layer, let's say we're using Photoshop, such that I have a Photoshop format, it goes down and then comes back up into his machine to where he can see it in Photoshop. Everything relies on the interaction between each of these individual layers when it comes to building this model. Now, the transport layer provides part of those functions. And the transport layer is also going to determine how we send our information. We're going to use the idea, excuse me, we're going to use the different ideas with regard to how we're going to send the information, whether or not we're going to send it reliably or whether we're going to send it unreliably. And we'll look at each of those points later on in our conversations. The other part here is the session layer. In the confines of the session layer, all its job is to create sessions. So it creates, manages, and terminates sessions such that we have these links that we're going to use to be able to communicate. Now, what will happen here, a perfect example is if web servers, for instance, they have lots of users. So what we're going to find here is that we need to be able to keep all of those communications open, and it's important for us to keep track of those. So let's imagine I'm connected to a web server and you're connected to a web server. We're both looking at different images. So I want to look at the image of the race car. You want to look at the image of the Sports Illustrated model that was sitting on the race car. All right, now, looking at that, what's going to end up happening here is the server is going to have to be able to keep track of who has to be able to see what image and what image they needed to see. And it's going to be through the session layer of the OSI model that process is going to take place, whereby using the OSI model, the server, the web server, is going to actually be able to say, oh, Terry asked for the race car and you asked for the sports model. So we're going to make certain that it sends the proper information to each of us based on our defined session. And it's through the session layer that this process actually operates. Now the other area here, and I'm going to change pen colors just so that we can mix it up a little bit, is going to be the presentation layer. Now the presentation layer. The further we go up the model, the more ethereal things get. But the presentation layer has one job, and that's to ensure that information that's sent to the application layer of one system is readable by the application of the other. So it's going to be my presentation layer that's going to make certain that anything that I send from Photoshop, for instance, is going to be formatted such that when you look at it on your Photoshop, it's going to be the proper image. So it's going to be compatible. And then lastly, we have this application layer, and the application layer is going to be where the user is interacting. So it's the layer in the model closest to the user, where the physical layer is the layer in the model that's furthest away from the user. And it's going to be where the applications run. Now, whether those applications are Photoshop, like I mentioned, a web browser, an email client, any of that is irrelevant. It all simply comes together to allow the system to operate. And it's through following this model uniformly across multiple vendors, across multiple devices, across multiple applications, across multiple drivers, that we get this idea of full interoperability between our different computers, our different network cards, all made by different vendors. So you can see this is exceedingly important, and Cisco's going to constantly drive it home. Now, like I said, there are two actual models. And what Cisco's going to want us to do is they're going to want us to be able to demonstrate the fact that we understand the Model A, which is the OSI model, versus the second model here, which is going to be the TCP IP model, the Transmission Control Protocol Internet Packet or Internet Protocol model. Now, when I was coming up, this was referred to as the DoD model, the Department of Defense model, because it was the model that DARPA used to make certain that whoever built devices to be used by the United States military or the federal government followed these rules so that they didn't have the problems where they got locked into one provider. They wanted to avoid this concept of monopoly. Now, when it comes to DARPA, they never left this. So what they ended up doing is they came up with a concept which is going to be an overlapping model, whereby we're going to see that each of these individual layers don't necessarily interact or overlap with another layer, but they do have corresponding layers. So inside the confines of the TCP/IP model, or the TCP/IP stack, we have the application layer, the transport layer, the internet layer, and the link layer. Now what we're going to find is the data link and the physical layer correspond to the link layer in the DoD or the TCP/IP stack. We have a one-to-one translation between networking. Remember, this is where IP is going to be running, and it's where our routing is going to take place. This is going to be where our switching takes place, just like we talked about earlier. Transport is the same, and then what we end up doing is we group the ULPs, the upper layer protocols, together into one layer inside the four-layer model referred to as application. So transport is transport in both models. Network is internet in the TCP/IP stack, and data link and physical combine to form the link layer in these confines. Now, what this doesn't do is this doesn't tell us what each of these does. So for the purposes of clarification, let's go to the whiteboard. Now, recognizing the simple fact, let me grab a pen color here, that we have these different devices, what we have to do is we have to understand that we have those four models. It's not letting me draw. I'll just draw with the other set of pens. And then I'll fix this between the breaks. So, looking at this, we have application. We have transport. We have the internet layer. And lastly, we have the link layer. Now, this always struck me as being more, maybe not as granular as the 7-layer model, but this always just came out to where it was so much more straightforward. And when we look at this, what we recognize is from the bottom up, the link layer in the TCP/IP model is responsible for a number of things. First of all, is it's going to take place, it's going to be responsible for ensuring that we have the same processes running as in the OSI model. And that's going to translate to the fact that it's going to be responsible for doing things like the physical characteristics of the link. Physical characteristics of the link itself. Now, what does that translate to? Well, the physical translation for this is going to be, it's going to configure how things are going to be accessed and how things are going to be controlled. Now, I want to kind of delve into this just a little bit, because we have to understand that when we take devices and we interconnect them on an Ethernet segment, as a general rule, back before we had these high-end switches that we're talking about right now, we used to have a problem, and that was only one device could talk at a time. And we had a technology that was referred to as carrier sense multi-access collision detection, and we also had another one that was referred to as carrier sense multi-access collision avoidance. Now, this one, collision detection, was Ethernet. The collision avoidance method was a technology called token ring, which is long died. It's gone the way of the dodo. It's nothing that we're going to have to worry about. But what we do need to understand here is that the terms that are going to be taking place with regard to the negotiation of how we're going to use this wire to share information all take place in the link layer of the TCP/IP protocol suite. Now, after that, the other primary one that we're really going to be spending the majority of our time discussing is going to be this idea of the internet layer. The internet layer provides the capability of routing data. So remember, routing data involves moving information between networks. So it's going to be at this layer that we're going to have the rules and governances in place to ensure that networks that are not on the, or devices that are not on the same network have the capability of intercommunicating with each other. Now, in the confines of the rest of our layers here, or the discussion, what we have to recognize is that it's going to do this based on destinations. So the destination of packets. So based on that, what we're going to end up realizing here is it's going to be the internet layer that's going to be responsible for moving data between link layer and transport layers. So just like we had here in the OSI model, remember I said the lower model provided services to the one above it. That's exactly what's happening. The application layer is serviced by the transport layer. The transport layer is serviced by the interconnection or the internetworking layer. The internetworking layer is served by the link layer, and then it's from the link layer that we go out on the wire. So again, we can see this organized, this hierarchical approach. And it's through the transport layer that we get our communication services. So this is where our session information takes place. So again, making certain that I can see the race car and you can see the sports model. So making certain that there is going to be some way to delineate as to who has requested what traffic so that we don't start getting crossover of information. All part of the transport layer. And then lastly, in this particular approach, the application layer. In the confines of the application layer, again, this is going to be where we have our APIs, our application-specific information and things that are going to be operating, where we're going to have our browsers, where we're going to have our webmail clients, or our, not webmail, but email clients, where we're going to have all of our application runnings. And it's also, oddly enough, correspondent to the operating system of the particular platform, so OS for our platform. So that would be Linux, it would be Mac OS or iOS or Windows. So again, we see how everything comes together in a holistic approach using these models so that everybody is following the same rules. But what we want to point out here is that everybody may be following the same rules, but we still have to take into account the fact that this information has to be passed from layer to layer. So what we're going to find here is that irregardless of what model I use, let's just say I use the TCP/IP model. In the confines of the TCP/IP model, I have application, I have my transport, I have my internet, and I have my link. So these are the 4 layers of this model. Now this is on my host, so on my PC, my computer, and I want to talk to another computer. Application, transport, internetwork, or network, excuse me. Did I say internetwork? Yeah, internet. Link, transport, and application. All right, and this is on your computer. And I want to pass information back and forth. Well, what we have to recognize, and I'll show this in a cleaner presentation here on the slides, and that is the fact that as I move data down my stack, so from my application to my transport to my internetwork or my internet down to my link layer, this is referred to as encapsulation. So I'm encapsulating the traffic, which means I'm going to be adding headers to it. So I'm going to have a layer 1 header, a layer 2 header, a layer 3 header, a layer 4 header. Now, when that goes out the link layer, bear in mind this is going to be a Ethernet connection for most purposes, going through switches, but we're using transparent bridging, so we can ignore it at this point, to communicate between your PC here and my PC over there. Now, when the information comes through, it's going to come through in ones and zeros. Well, that information is going to arrive at your link layer, and it's going to be reassembled into the ones and zeros on that side, and it's going to be passed up the model. Now, what we're going to find here is this is a process referred to as de-encapsulation. Because all the headers that were added, so I've got my layer 4 header here. Here I add a layer 3 header with my layer 4 header. Down here, I add a layer 2 header with my layer 3 header and my layer 4 header. And down here, I'm going to be adding a layer 1 header with my layer 3 and my layer 2, my layer 3, and my layer 4 headers. So as you can see, it's getting bigger. Why? Because I have to add information such that when I pass it to the next layer, it's going to say, okay, I'm going to take my layer 1, it's going to arrive here as L1, L2, let me get my head out of the way. It's going to arrive here L1, L2, L3, and L4. Well, what's going to happen is it's going to remove the L1 header, and it's going to take this, and it's going to pass it up to the internet layer. So I'm going to have layer 2, layer 3, and layer 4. The layer 2 header tells this layer what to do. So it says, okay, I'm going to process the information. I'm going to go in and do virtual reassembly. Then what I'm going to do is I'm going to drop my layer 2 header, and I'm going to pass it to the next layer up, where that's going to say, oh, now I've got layer 3 and I got layer 4. The layer 3 instructions tell me what to do with it, and I pass it up to layer 4 with the layer 4 header, so that what happens is that I have same level networking communication. And what we're going to recognize, or we're going to need to learn here, is that each of these layers employs something called a PDU. A PDU stands for a Protocol Data Unit, and we call them different things. All right, when we start looking at how this is going to be implemented, at the application layer, we're going to have data. That's what we're going to call it. All right, at the transport layer, we're going to have different names. It's going to go all the way down, depending on whether or not you're talking about the OSI model versus the 4-layer model. But we'll look at that in the confines of the actual presentation. So let me bring back up that, and we'll go through it. Because what I want to do is I want to visit, or I guess technically revisit, the idea of this encapsulation, de-encapsulation process. And this is exactly what's happening. As I said, encapsulation. Encapsulation means I'm adding headers. So as you can see here, notice I have my other header information, I have my user data. So my user data generated here and got passed down to the next layer, where we added, or it has the layer 4 header on it. As I send this information down to the internet layer, what ends up happening is I add the layer 3 header on it, moving all the way down ultimately until I add the layer 2 header and I send everything out. What we can see, and I'll move myself out of the way, notice up here we have the encapsulation process. So let me walk through this. I create a user data. Let's say it's a picture. Then what ends up happening is the application layer passes it down to the transport layer. Well, the information, when it hands it down, it's going to add any header information used to compile the image. And then what's going to happen is that it's going to have my layer 4 header on it. Then when I pass it down to the internet layer, I'm going to take everything that was handed to me, and then I'm going to put my own layer 3 header on it, all the way down to where it arrives at layer 2, where ultimately it's going to get sent out on the wire, such that it's going to traverse the system. Now, we also have this idea of an FCS. That's file checksum. Now, what ends up happening here is that I'm going to run an algorithmic computation. So I'm going to take all of this information right here, and I'm going to run a mathematical computation against that information. And what I'm going to do is I'm going to come up with a numeric value. Well, that numeric value is going to get put here, and it serves a special purpose. Because what we're going to find is as I send this across the wire, if someone were to intercept this packet, or if something were to happen as it's being transferred across the wire, what can happen is that information can change. So this payload information that we're talking about right here could definitely be manipulated, either intentionally or unintentionally. Now, what we do is we use that FCS, that file checksum, so that when it arrives on the other end and we go through our de-encapsulation process, the first thing that we want to do at the link layer is we're going to make certain that we have this concept, this deployment, whereby we're going to be able to check the information to see if it's been fiddled around with. So let's look at exactly what's happening. Now, when we go through here, we have where we have our network access layer. That's going to be our link layer here, going all the way up to the internet to transport to the application. So we can see that this is moving up the stack. Now, by moving up the stack, what we're doing is we're governing the idea of de-encapsulation. So we're removing all of those headers. I'm going to take my head out of the way so that we can look at it. And the first thing that's going to happen is I'm going to take this checksum, the file checksum that was sent with the file. Then what I'm going to do is I'm going to take the entire user data, I'm going to pop this checksum off, and I'm just going to put it in a buffer. I'm going to store it. Let's say it's X. That's the mathematical value. Then what I'm going to do is I'm going to run my own computation against this information, header 2, header 3, header 4, any other header information, as well as the user data. And then what I'm going to do is I'm going to come up with my own value. my own algorithm. Same algorithm that was run when it was encapsulated will be run when it's de-encapsulated. If these two values match, then the data is going to get handed up the layer. If they don't match, then whatever error recovery process we have, either asking for the information to be resent or just dropping the packet, that will take place. But that file checksum allows us to make certain that nothing happened to the data in transit. The moment it goes up to the next layer, it arrives with a layer 3 header that has all of the instructions and information as to how the next layer should handle it before it hands it up to the next layer, to the next layer. Ultimately, it arrives as the picture that was sent that can be viewed on the receiver's PC. So looking at this whole thing, encapsulation and de-encapsulation is exceedingly important, and Cisco is definitely going to want to make certain that you know exactly what you're talking about when it comes to this entire process on the exam itself. It's not overly difficult, but it is something that you need to commit to memory, and it's something that we need to be mindful of. Now, here is what I was talking about earlier. I was talking about PDUs, and I was talking about same level computing or same level communication. Something referred to as peer-to-peer communication. So the communication, the information that's contained in the header that was encapsulated as it was sent down my PC, and the information that was exposed when the lower layer here removed its header and sent it up, those header informations ensure that everything is going to be communicated. And the information that is communicated is going to be this peer-to-peer communication. And what we have is we have different values here. Notice here, they're using the actual term link. But let me grab a pen. Oops, I hate that. Now, what we see, first of all, is these PDUs. Again, that stands for Protocol Data Unit. Now, PDUs just define the information that's being exchanged. So when it's application layer to application layer, it's called data. When it is transport to transport, like I said, it's called a segment. When it's network to network, we refer to it as a packet. And when it's link to link or network access to network access, it's called a frame. And that's very, very important. This is definitely something that I would expect Cisco to ask us in the confines, either via, drag and drop, via a multiple choice question. This is definitely a ripe field with regard to something that Cisco is going to want us to know, because it is very important. It's very important because if I'm communicating to you and we're both network professionals and I've got to go home and I'm handing a job off to you, if we do not use the same vernacular to define problems and situations or things that we're dealing with, you don't know what I'm talking about. But if I say frame, you know I'm talking about a layer 2 problem. If I say packet, you know I'm talking about something to do with layer 3 routing. If I say segment, you know I'm talking about something in the confines of the transport layer, and vice versa. And that's why this is so important, because it gives us a unified terminology, a unified verbiage that we can employ to exchange information as professionals about our infrastructure, and it's definitely something that I would expect Cisco to test you on. So with that being said, I'll see you guys in the next lesson. Bye-bye.